Good morning, everybody, and happy Friday. It is December 15th. For a lot of you, perhaps it is your last day of school before the winter break. It is for me, and so I'm happy to be here bright and early this morning. It's actually pitch dark out, but and it is time for the 15th episode of our AP Calculus Free Response Question Advent Calendar. Let's begin by getting into the chocolate, and I've already spotted the 15th compartment. I think that's kind of a sign of good things to come. 15th compartment, it's right here with the pine cone, which is snow-capped. Very nice. I don't know what those berries are like behind the pine cone. I guess it's not part of the pine cone. Anyways, while I get into this chocolate, I'll put today's free response question on screen now. Today we're doing it really straightforward, like this is as standard as it gets. Pretty standard derivative problem. We're going to find a tangent line, and I think, the end of the problem is an integral. A little bit of u-substitution. No spoilers. Sorry, give it a try yourself if you don't want spoilers. I'm sorry, it's just what I do. All right, we got this green chocolate. Let's get into this bad boy. Whole lot of calories, all these chocolates. All I do is record these videos in the morning and then exercise the rest of the day to work off the chocolate. That's pretty good. Pretty normal, pretty standard. Standard fare. All right, let's do the calculus. This is free response question 4 from the 2012 AP Calc AB exam. Let's read it. The function f is defined by f of x equals the square root of 25 minus x squared, which you may recognize as the equation of the top half of a circle centered at the origin with radius 5. And x is between negative 5 and 5. Part A is very straightforward. We're just looking for the derivative f prime of x. So let's go ahead and find the derivative of f of x. In order to do that, it may help to rewrite f of x first. Note that a square root is the same as a power of 1/2. So the square root of 25 minus x squared is the same as 25 minus x squared, all to the power of 1/2. And this makes it more clear that to find the derivative, f prime, we'll simply need to use the power rule and the chain rule. We have to use the chain rule, of course, because f of x is a composite function. The outside function is this power of 1/2. How do you take the derivative of something to the 1/2? Well, you have to bring that power of 1/2 down as a factor, leave the inside function unchanged, 25 minus x squared, and then reduce the power by 1. So now the power is negative half. That's just the power rule. But then by the chain rule, because we have a function inside of this, 25 minus x squared, we also need to multiply by the derivative of that function. And the derivative of 25 minus x squared is negative 2x. And this is f prime of x, although there is a little bit of simplification we can do. We can bring the negative to the front, and of course the 1/2 and the 2 cancel out. So there is our answer. F prime of x equals negative x times 25 minus x squared to the negative 1/2. Again, we wrote the negative and the x out front, and the 1/2 and the 2 cancel out. So that's our answer for A. Part B. Write an equation for the line tangent to the graph of f at x equals negative 3. Okay, for a tangent line, we need two things, a point and a slope. For the slope, we will be able to use the derivative that we just found, and the point is even easier than that. The point, we know, has an x-coordinate of negative 3. To find the y-coordinate, we just need to plug negative 3 into our function, because we know the tangent line has to meet the function at x equals negative 3. So plug negative 3 into the function to see what the y-coordinate has to be. Here's our function. Let's plug negative 3 into it. F of negative 3 is going to be the square root of 25 minus negative 3 squared is 9. So this is the square root of 25 minus 9, which is the square root of 16, which is 4. So the point that our line is tangent to is negative 3 4. That's where our tangent line is intersecting the curve. We can find the slope of the tangent line at this point by plugging -3 into the derivative, which we just found. So let's plug -3 into this derivative. That's going to be -3. Remember, there's that negative out front. And then in parentheses, we have 25 minus -3 squared, which is just 9, and this is to the power of -half. Now what is this? Well, the negative and the front cancel out, so we just have a 3, and let's go ahead and write this as a fraction. This has a negative power, 25 minus 9, so I'm going to give it a positive power by putting it in the denominator. Then we would have this 3 in the numerator, and in the denominator, we would have 25 minus 9 to the 1/2. 25 minus 9, though, is 16, so that would be 16 to the 1/2. But a power of 1/2 is the same as a square root, so this is the same as 3 over the square root of 16. The square root of 16, of course, is just 4, so this is 3 over 4. That is the slope of our tangent line. Then we can use point slope form to write the equation of the tangent line. Y minus the y coordinate, which we found to be 4, equals the slope, which we found to be 3 over 4, multiplied by x minus the x coordinate, which of course is -3. But x minus -3 is the same as x plus 3, so let's just write it that way because that looks nicer. And that's it for part B. Moving on to part C. Let g be the function defined by g of x equals a piecewise function. It is equal to f of x when x is between -5 and -3 inclusive, and it's equal to x plus 7 when x is greater than -3 and less than or equal to +5. The question is g continuous at x equals -3, which is where its definition switches. At -3, it switches from f of x to x plus 7. So is it continuous there? To answer this, we must use the definition of continuity. The definition of a function being continuous at a point, let's say -3 in this case, is that the limit of g of x as x approaches -3 from the left should equal the limit of g of x as x approaches -3 from the right, and those one-sided limits both have to equal the function's value at -3. That's what it would mean for g to be continuous at -3. Now, when x approaches -3 from the left, g of x behavior is f of x, because x approaching -3 from the left means that x is less than -3. So the behavior of g of x would just be f of x. Now, what is it approaching then from the left? Well, we can find that by just plugging -3 into f of x. We've already done that, and we know that it would equal 4. So the limit of g of x as x approaches -3 from the left is 4. Now, what about from the right? If x is approaching -3 from the right, then the behavior of g is here, because it is here where x is greater than -3, so it can approach -3 from the right. The behavior of g of x is that it's x plus 7. So what's the limit from the right? Well, plug in -3. -3 plus 7 is +4, which was the same as the limit from the left. Finally, if we actually plug -3 into the function g, what does it actually equal at -3? Well, it is equal to f of -3, because remember, it's on this piece of the function where x is allowed to equal -3. So g of -3 we see is just f of -3, which is 4. So yes, it is continuous, and let me write those details out. Here's the argument we just went through. G is continuous at x equals -3, and we justify this using the definition. That's how we were asked to do it. We know that the limit of g of x as x approaches -3 from the left is the limit as x approaches -3 from the left of f of x, because that's g of x's behavior when x is less than -3. It behaves like f of x. And this limit we find by just plugging in. It turns out to be 4, which is also the value of g at -3. It is 4. Now, if we approach -3 from the right, we found that it also equaled 4 when it's behaving like this line, x plus 7. It's also approaching 4 as we go to -3 from the right. So the function's value equals the limit from the left equals the limit from the right. Indeed, g is continuous at x equals -3. That is part C. So let's go ahead and finish with part D. Find the value of the integral from 0 to 5 of x times 25 minus x squared dx. Of course, you can see f of x is showing up in this integral, which is why this is another part of this problem. All right, I've just copied this integral down. Here is part D. You should notice at a glance that this is a pretty easy u-substitution problem. If we let u equal 25 minus x squared, so I'll write that, u equals 25 minus x squared, well then du is just negative 2x dx, which practically matches the remainder of the integrand, x dx, and we can make them match exactly if we multiply both sides of this equation by -half. If we do that, then on the left we have -half du, and on the right we just have x dx. So you can see how we'll be able to make that replacement and cleanly write this integral in terms of u. One other thing I'll point out, notice if this x was not here, this x that enables us to use u-substitution, then you would have to notice that this is the equation of the top half of a circle, like I mentioned earlier. And then finding the area underneath it is pretty straightforward since its radius is 5 and we're integrating from 0 to 5. So you'd actually be looking for the area of a quarter circle in that case. It'd actually just be a very straightforward geometry problem if you recognize that. But that's not the problem we've got. We've got this x here, so let's proceed with the u substitution. So this is the integral. We can rewrite the bounds so that they are appropriate for u. If x is 0, then u is 25 minus 0 squared, which is just 25. So in terms of u, the lower bound is 25. Now if x is equal to 5, then u is 25 minus 5 squared, which is 0. So the upper bound for u is 0. Now what are we integrating? We're integrating the square root of u, because 25 minus x squared is u, and then the x dx is getting replaced by half du, with of course a negative as well. Let's just bring that negative out front, and you know what? Let's put the -half out front as a whole, and then we just have the du there. Okay, let's proceed with this integral. This is pretty straightforward. Again, you should recognize that the square root of u is the same as u to the 1/2. So this is a simple reverse power rule integral, you might say. We will have a -1/2 out front, and then to do the reverse power rule, we increase the power by 1. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. So u to the 3/2. Then divide by this new power. Dividing by this fractional power is the same as multiplying by its reciprocal, 2/3. And we are evaluating this from the lower bound, 25, to the upper bound of 0. All right, we'll proceed with this. We still have that -half out front. If we plug the upper bound 0 into this, what we're going to get is 0. And then subtract, plugging in the lower bound. So we're subtracting 2/3 multiplied by 25 to the power of 3/2. Finally, this is -1/2. The 0, of course, doesn't matter. 25 to the 3/2 is the square root of 25 cubed. The square root of 25 is 5, and 5 cubed is 125. So what we have in brackets, which I'll just use parentheses now, is -2/3 multiplied by 125. Again, we got that by first applying the power of 1/2, which is just a square root. Square root of 25 is 5. And then we apply that power of 3, cubing the 5, to get 125. All right, we're nearly there. The negatives will cancel out. In the numerator, we would have 2 times 125, which is just 250. And in the denominator, we have 2 times 3, which is just 6. Now we just have to reduce this fraction. We can reduce both things by a factor of 2. The numerator divided by 2 is 125, and the denominator divided by 2 is 3. We, of course, could have just canceled the 2's up here to begin with. And hey, look, that's our answer, and that completes our solution to free response question 4 from the 2012 AP Calc AB exam. Let me know in the comments if you have any questions, and be sure to check out the full AP Calculus free response question advent calendar. We've got a bunch of episodes already, hours of great calculus free response questions, and still hours and hours left to go. Christmas is still over a week away, so hey, make sure you subscribe. Check back tomorrow when I will see you for another episode of our advent calendar. Thanks for watching.